Hi everyone, and thanks for tuning in tonight to learn how we know the universe is expanding. And my name's Jonathan Park, as you can probably see from the first slide there. Now, before we get started, let's quickly go through some of the main points for tonight. First of all, we know the universe is expanding. It's getting bigger and bigger. And this means space itself is expanding, new space is coming into existence. Now, working backwards from what we see now, we arrive at a time 13.8 billion years ago, when the universe was in a hot, dense state. This was a moment in time that we called the Big Bang. It's important to remember that the start of the universe was not an explosion in space. Instead, the universe started with a rapid expansion of space. There actually was no bang. In fact, the phrase Big Bang was actually coined by steady-state theorists to mock the idea of a starting point. It was Fred Hoyle in 1949 who apparently said, "The hypothesis that all matter of the universe was created in one Big Bang at a particular time in the remote past was irrational." So the words were originally meant to be in a derogatory sense. Little did he know that he'd coined the phrase that would be used for so many years after that. Now, astronomy is a science, and in science, we can't just say something is so and that's that. We need evidence and theories that make predictions that we can test. So tonight, I want to show you how astronomers or cosmologists know all of this. But let's start with some science and see what we actually currently know. So what do we know? Well, the universe began 13.8 billion years ago with the Big Bang, and it's been expanding ever since, as you can see from this graphic here. For the first 7 or 8 billion years, the expansion was actually slowing down, and then it started speeding up due to something called dark energy. But dark energy is not required for the universe to expand. It would still be expanding, but the expansion would actually just slow down, be slowing down forever and ever. A universe with no dark energy could eventually stop expanding and then collapse in a big crunch. Anyway, the main point here is that for tonight, you can forget all about dark energy. Now, it's interesting to see what we used to think about the universe compared with what we know now. Before about 1917, the Milky Way was generally assumed to be the whole universe. There were a few different models, like this one from Jacobus Kapteyn, but the universe was assumed to be static, not expanding or contracting. We were usually placed somewhere near the middle, about here. Andromeda might have been assumed to be about here somewhere. Some models showed spiral arms, like this one from Cornelis Easton in 1913, which you can see is looking a bit more like our modern picture of the Milky Way. Here's our sun here just off the centre as well. Now, we currently know that we are just one of hundreds of billions of galaxies in an expanding universe. In this animation on the right, using data from the Sloan Digital Sky Survey, there are about 400,000 galaxies. The individual galaxies in the animation are actually drawn a lot larger than they would be, otherwise they'd be too small to see. And I should say this video is not showing expansion, it's just showing a fly-through at the current time. And of course over here is the modern idea of the shape of the Milky Way, with our sun about 26,000 light years from the centre. So now let's have a look at things moving through space. Here's a random selection of stars in our own Milky Way galaxy, moving through space at various speeds. Within our galaxy, space is not expanding, so things are simple. Well, relatively simple. And on the right here, we have some of the galaxies in our local group. These are moving through space relative to each other due to gravity. They will all eventually collide and form a supergalaxy in billions of years. Relative to us, these two are moving towards us, and this one is moving away. More precisely, the Triangulum galaxy is moving towards Andromeda, and the pair are moving towards the Milky Way. This is all happening as they're all orbiting a common centre of mass. So in this small part of the universe, space is not expanding because the objects are bound together by gravity, overcoming the expansion of the universe. Just for perspective, here's a map of the local group of galaxies and some other nearby galaxies. That's us there, and Andromeda just over here, about 2.5 million light years away, and the Triangulum galaxy over here. The centre of the local group is about here between the Milky Way and Andromeda, and the whole group is about 6.5 million light years across. So a group of galaxies is a gravitationally bound system of galaxies with between 3 and 30 bright galaxies. If there's more than 30 bright galaxies, it becomes a cluster, or it's named a cluster. In the bigger picture, when there's enough space between the galaxies or the galaxy clusters, they will not be bound together by gravity. This means the expansion of the universe will carry them away from each other. But in this case, these clusters are not moving through space. Space is expanding between them, making the distance between the clusters get bigger. So here's a two-dimensional universe, a whole lot of galaxies on the surface. Now, if we just rotate it around a bit, and now we're going to start expanding our universe. New space will appear between the clusters. And so as space expands, you can see the clusters and the galaxies have remained intact. They've stayed the same size. But also remember, they're not moving through space. Instead, the space between them is expanding, and so on as the universe continues to expand. You can also see not only that the galaxies and the clusters are the same size and further apart, the distance between each cluster increases by the same ratio over the whole universe each time for the general expansion. So in the time it took these two clusters to move twice as far apart, everything else also moved twice as far apart. And that happens right throughout the universe. So often a rubber sheet being stretched is used as an analogy for the stretching or the expansion of the universe. Now, of course, stretching a rubber sheet, you know that it will thin out as it gets stretched, keep thinning out more and more until it finally snaps. The expansion of space, in the expansion of space, nothing actually thins out. New space essentially is forming as it's stretched. And of course, the universe has three dimensions of space, not just two. So this is all happening in three-dimensional space, not on a surface, and it's expanding in all directions. That way, up, down, left, right, in this very small part of the universe that's shown here. Now you might wonder, how could anyone possibly tell if a distant object in space is moving away from us or towards us, and how fast it's moving? Well, a good way to explain this is to start with something called the Doppler Effect. Here's a police car. It's not moving, but its siren is going. A person standing in front of the car here will hear the siren at its normal pitch, and so will a person standing behind it. These blue circles represent sound waves. Now, we're all familiar with the change in pitch of a sound when the source is moving towards us versus moving away from us. When the police car is moving towards us, you can hear a higher frequency because the sound waves are bunched together. So you can see the sound waves being bunched together here. And this creates a shorter wavelength, which is a higher frequency or higher pitch. And in the other direction, the waves are more spread out, resulting in a lower frequency or a lower pitch. Now, a similar thing happens with light. Here are a couple of green lasers with a wavelength of a wavelength of 550 nanometers. A nanometer is a billionth of a meter. And so the wavelength from here to here is 550 billionths of a nanometer. This picture at the bottom is just giving an idea of the wavelengths of visible light. So you can see with longer wavelengths here towards the red end, and the shorter wavelengths toward the blue end. And as we go out into the ultraviolet, the wavelengths are shorter and shorter, and towards the infrared, the wavelengths are getting longer and longer. But let's say we have two observers, Bob and Rob. They both see the laser light as green. Now, if we start moving the top laser towards Bob at about, say, 60,000 kilometers per second, which is about 20% of the speed of light, in the direction the object's moving, just like we saw with sound, the wavelengths are bunched up. And so the wavelength is shorter and the frequency is higher. In this case, the light becomes blue. So Bob sees the light as blue, and we say the light is blue shifted. So now blue shifted means toward the blue end of the spectrum. It doesn't necessarily have to change to blue. It depends on the speed. If it was going any faster, it could have become violet or ultraviolet, or even further out into the X-ray at very high speeds. And it's the same in the other direction. The wavelength becomes longer, so the frequency is lower. In this example, the light becomes red, and so Rob sees the object as red, and we say the light has been red shifted. Now again, it doesn't necessarily become red. At lower speeds it might have become yellow or orange, or at higher speeds infrared, microwave, or even radio. At much lower speeds, of course, the effect is much more subtle. And you might wonder, if we don't know what colour the light was to start with, how can we know how fast it was moving, or even if it was moving at all? So how does Bob know, for example, that the laser wasn't blue and not moving, or maybe Rob, that the light wasn't red and not moving? With lasers, actually, it would be impossible, because the light from a laser is essentially a single pure wavelength. But stars radiate with a whole range of wavelengths, not just one colour. Here's a white star like our sun. It radiates in all the colours of the rainbow, as well as infrared and ultraviolet and beyond. If you don't look too carefully, splitting the light up here looks a lot like a continuous, it does look like a continuous spectrum. And the light can be split up, as you know, using a prism or various other devices. Now, if you look more carefully, you'll find lines, these little black lines, where particular wavelengths are missing. And this is actually the spectrum of our sun. These missing lines are actually due to particular wavelengths being absorbed by atoms in the sun's atmosphere. And for each element, or each type of atom, it has its own fingerprint. And let's have a look at a simple example here. This is a light source emitting all the colours. And over here we have a cloud of hydrogen atoms. Hydrogen atoms absorb particular wavelengths, and they re-emit them in all directions, letting all the other wavelengths through unimpeded. So when we look at the light through this cloud, certain wavelengths here are missing, or mostly missing. Now these are called the hydrogen absorption lines in the visible part of the spectrum. They are the frequencies that are re-emitted in other directions by the hydrogen atoms. So you can see this red colour here is missing as it's been absorbed and then re-emitted in different directions, similar to this light blue colour and the dark blue and violet colours as well. And here are the strong sodium absorption lines. And not surprising, this is orange, as you've probably seen the sodium street lights, which emit this colour as the electrons or the atoms in the sodium gas in the street lights are excited, and then they emit this coloured light. So a similar kind of thing, just the other way around. And helium, a few lines in the visible spectrum for helium. Now, altogether we get this. We can add up all these lines and we get this kind of a picture here. To keep things simple, I've just used these three elements for the example. In reality, there's heaps more. So here's our star again. It's not moving relative to us. So have a look here at the spectral lines. You can see they're all in the expected positions, as if they had been emitted by a light or a lamp that wasn't moving. And here's an identical star. So if you have a look at the spectral lines here, you can now see that these have all been shifted towards the blue. The light has been blue shifted. So all the wavelengths have been shortened, so the star is moving towards us. It's a bit like the laser where we saw just the green light being squashed, or the wavelengths being shortened into the blue light. Now, we can also tell how fast the star or the object is moving from the amount of light, from the amount the light's been shifted. In this case, plugging the shift into a special formula gives us about 15,000 kilometers per second towards us because it's been blue shifted. And here are two more identical stars. Have a look at these spectral lines again. You can see that for this star, or this the star here, the lines have been shifted slightly to the red, and for this star they've been shifted even more. So if we take our laboratory reference, we can see quite a large shift in the absorption lines there. And this amount of shifting gives us about 6,000 kilometers per second away from us for this star, and 17,000 kilometers per second away from us in the other star. Now, for a whole galaxy, there will be a spectrum as well. Here's an example with 3 different sample galaxies. At the bottom, you can see our laboratory reference again for a object that's not moving. And for this first galaxy, you can see that there's a tiny redshift in the main lines here. So we can see that this one is moving away from us. And for this next one, you can see the lines are a lot more redshifted. This line is out here and these lines are over here. And it's moving away from us at obviously a greater speed than the first one. And even more so for the top one up here, where you can see these lines are quite shifted compared to the original galaxy at the bottom. Now, the spectral lines for a galaxy are a combination of all the stars in the galaxy or the part of the galaxy that's being observed. So far, so good, but if you remember from earlier, I said the distant galaxies are moving apart not because they're moving through space, but because space is expanding between them. And while the Doppler effect occurs for things moving through space, such as our galaxies in our local group, which are moving through space, it is not the cause of redshift in expanding space. And here's a little graphic of expanding space. Let's have a look at an example here of cosmological redshift. So this is a really neat type of redshift where light is stretched by the expansion of the whole universe. Now we have our 2 galaxy clusters here, and here's some light being emitted from this cluster. It starts out at a particular wavelength, and as it travels through expanding space, you can see the clusters are moving away as the space expands between them. This light is being stretched as it's moving through this expanding space to longer and longer wavelengths, and you can see it's towards the red. And so this is called cosmological redshift. You can see it started as a particular wavelength and has ended up as a much longer wavelength here. Now, again, it doesn't necessarily change to red. I've just used these colours as an example. For very distant galaxies, it can actually shift all the way into the infrared. The James Webb Telescope that has previously been launched and will be giving us some data soon. We'll be able to see some of these galaxies that have been so shifted that they're in their infrared range now. Now, a bit of a summary of these 2 types of redshift together is quite handy to look at. In this top one, each line is a different time, so we start off at 0 and move through time. You can see that the light has been shifted as it's left this galaxy here, but as it's traveling through non-expanding space, it's not being stretched anymore because the space is not expanding. So these things are moving through space, and as it reaches the final galaxy here, it's remained the same wavelength as what it was when it was originally stretched. Cosmological redshift, on the other hand, on this bottom image here, over time you can see as these galaxies are moving apart, as we saw in the previous example, the light is getting stretched as it moves through space. So you can see the difference in these 2 here. So just continually stretching through expanding space. Now let's have a look here at a laboratory reference at the top here and a distant galaxy. We can look at these spectral lines which have been slightly redshifted. You'll see that here. And so the galaxy is definitely moving away from us, but You can't actually tell if the redshift is cosmological or Doppler or some combination, but that's actually okay for closer galaxies where the redshift is very small. The answer actually comes out about the same. So for this galaxy example here, the redshift is about 0.006, a very small amount. And so it's moving away from us at about 1800 kilometers per second. And that'll be the same result using either interpretation. Now, armed with all that science, we can now understand how we know what we know. This is a nebula. This is the Trifid Nebula. And here's another one, the Orion Nebula, which you're probably fairly familiar with. A nebula is a cloud of gas and dust, and the word nebula actually is actually Latin for mist or cloud. Nebulae are found throughout the galaxy and other galaxies, and with a small telescope they might look like this. This is the Lagoon Nebula, here's the Trifid Nebula, and here's the Orion Nebula. And you can see they do look like misty clouds. Looking through telescopes around the 1900s, other galaxies might also look like this, spiral-shaped clouds. And in the early 1900s, these were thought to be within our Milky Way galaxies, and they were called spiral nebulae, which means they were thought of as spiral-shaped star-forming regions. Although there were actually some astronomers who thought they might actually be other whole galaxies, or island universes they called them. So we were thought to have been living in an island universe, and a few thought that maybe these were other island universes, but it was far from agreed upon at that stage. So astronomers back in those days saw a large number of nebulae, including the spiral nebulae. You can see that to the people back in those days, they might have all just like clouds of gas and dust within our own galaxy. And as I said, there was some debate as to whether the spiral nebulae were actually other island universes or whole galaxies. And along comes Visto Schleifer, an American astronomer, 1875 to 1969. In the early 1900s, Dr. Schleifer began studying nebulae, and from 1912 he discovered something really interesting about the spiral nebulae. Using spectroscopy, which we looked at earlier, he found the redshift or blue shift of these objects. Now this Z here means redshift, so that's the symbol for redshift. Now using the redshift, he calculated how fast these are moving. He discovered that Andromeda, which they call the Andromeda Nebula, and a few others were moving towards us. But he found most of the spiral nebulae were moving away from us. So he didn't know the distances to these spiral nebulae, but he did notice that the smaller, fainter ones were actually moving away faster than the brighter, bigger ones. But it wasn't actually guaranteed that the smaller, fainter ones were further away. Maybe smaller ones could just move faster. And if we compare these speeds with stars in our galaxy moving relative to us closer to just in the tens of kilometers per second, you can see that the speeds of these galaxies was much higher than the speeds of the stars, in the hundreds, even the thousands. So 1100 kilometers per second is a lot higher than these 10 kilometers per second for the stars that we see. And so Schleifer interpreted the redshifts as the Doppler effect, as we saw earlier, because at that stage no one really thought about expanding space. Of course, things should be moving through space. And here's some of his results here. The minus sign means moving towards us, and the plus means moving away. And so, for example, here's Andromeda here with a velocity of minus 300. So that was calculated to be moving towards the sun at 300 kilometers per second. If it had only been, say, 50,000 light years away, it would reach us in 50 million years. So if it actually had been within our galaxy, it would be reaching us in 50 million years' time. This one here, the 1100 kilometers per second away from us, if that was in the galaxy, that would be leaving our galaxy in about 20 million years. You probably notice, or you might notice, that the speeds here he's given in kilometers. Of course, it should be kilometers per second. strictly speaking being a speed, not a distance, but he just put kilometres in his paper. And as I mentioned before, the Doppler interpretation is fine here. It's actually the same as the cosmological for very small redshifts of less than, say, 0.01. You can see that the redshifts of these objects were quite small. Now we'll meet Edwin Hubble, whom the Hubble telescope is named after, and also famous for the Hubble Constant and Hubble's Law. Now this is actually now called the Hubble-Lemaitre Law, which I'll explain to you why that has been renamed a little bit later on. And I'll explain this relationship as well. Now, Hubble calculated the distances to the objects Schleifer had studied, plus some of his own data, and he plotted the distance against the velocity in the famous Hubble diagram. And from all of this, he showed that the more distant objects here were moving away faster than the nearer objects. And if we remove the lines from the graph here, before he put the lines on, he would have had this kind of a plot. So he did pretty well to make the assumption of a straight line relationship with these, rather than maybe some weird curve. So it's pretty intuitive there, I guess. Turned out he was right though. So a couple of things to look at here as well. Like Schleifer had done, Hubble put kilometres instead of kilometres per second as the speed. And if you're wondering what a parsec is, it's probably not something everybody's familiar with. It's about 3.26 light years. So a megaparsec, a million parsecs, is about 3.26 million light years. And 2 megaparsecs is about 7.5 million light years. So Hubble found that for every megaparsec of distance, the recession speed of the galaxy, the speed it seemed to be moving away from us, was an extra 500 kilometres per second. Well, the range was actually about 500 to 530 kilometres per second per megaparsec. This is what we now call Hubble's constant, but Hubble just called it K back in the days there. To find the distance to these galaxies, Hubble used stars called Cepheid variables. This is a type of star that changes brightness by pulsating at a frequency relative to its brightness, and it also actually changes size. So you can see here, these are the days, this is just an example Cepheid variable. Over the days, the brightness increases and drops and increases and drops at a regular frequency. So taking the period, the time between the brightest times, and comparing it with the brightness of the star, the distance can be calculated because the absolute brightness can be calculated from the relationship here. So these stars are what's known as a standard candle. So by looking at how much dimmer a Cepheid variable appears to be than what it should be, its distance can be calculated. So if we use a standard Cepheid variable and we know that it's, say, 10 parsecs away, it should be a certain brightness, then we see another one that's a quarter of the brightness, we know it's twice as far away. Or if it's a ninth the brightness, it's 3 times as far away. Hubble couldn't actually see Cepheid variables in some of the galaxies, so for those he actually made the assumption that the brightest stars in each galaxy should be about the same. And he also used the overall galaxy brightness when the other information wasn't available, or a mix of the different methods. Now, that's not perfect using the brightest stars and the overall galaxy brightness, but it was good enough, and he certainly came up with the correct answer, the correct relationship anyway. Now, you might wonder how we could work out the distance and brightness to the first Cepheid as a comparison. Next month, Chris is going to go into some more detail about distances and tell you how this is done. And it was Hubble's discovery of Cepheid variables in Andromeda that finally proved that the spiral nebulae were whole galaxies and not just star-forming regions in the Milky Way. The Cepheids had been found in the Milky Way galaxy, and seeing them in another galaxy or other galaxies was the final proof that we were just one of many galaxies in the universe. So we'll just go back to the Hubble constant again. Hubble's calculation was about 500 kilometres per second per megaparsec. But the problem was there's actually two types of Cepheid variable, and they have a different period luminosity relationship. So some confusion over the type meant that the distance was out by about a factor of 7. And so if we adjusted that, this distance here would be about 7 megaparsecs and this about 14 megaparsecs. And that would actually give the Hubble constant somewhere between 70 and 75, which is actually pretty good since the latest calculations are between 65 and 75. So he was pretty much on the right track, and if he'd had the correct Cepheid variable, it would have been just about perfect. More modern figures using something called a Type 1a supernova give us this plot here. So you can see Hubble's original data here just filled this tiny little patch at the bottom. And with the correction we saw earlier, it actually follows on quite nicely. Type 1a supernova is an exploding white dwarf star, which is another standard candle. They take matter from a partner star, and once the white dwarf star has accumulated enough matter, it reaches a critical mass and explodes in a supernova. And that's also a standard candle and can be used for further out distances than the Cepheid variable. Hubble did actually do some more measurements later, out to speeds of about 20,000 kilometers per second. Now the distances were still not correct, but the important part at this stage was the straight line relationship between the distance and speed. So you can see where he had 10, 20 and 30 megaparsecs or million parsecs. Should have been about 80, 160 and 240. But look, it's really amazing that he's still got this amazing straight line relationship, and the fact that this is carrying on throughout distance, throughout the universe. Now, I mentioned before the Hubble-Lemaitre law being the new name for the Hubble law. It was in 1927 that Georges Lemaitre was the first to actually propose that the whole universe was expanding. He concluded this from Hubble's data and a bit of his own information, but he also combined it with Einstein's general relativity and field equations. And it was his 1927 paper, which you'll actually notice is 2 years before Hubble's paper with the Hubble diagram. In 1927, he said in the conclusion, the recession velocities of extragalactic nebulae are a cosmical effect of the expansion of the universe. And this is the original paper in French, which was not well known, and so not a lot of people saw it. It's been translated a couple of times. The latest translation I found is 2013, where you can see talks about the universe increasing radius due to the radial velocity of the extragalactic nebulae. And so through the work of all these astronomers and physicists and more, it was pretty clear the universe is expanding. We had Visto Schleifer with his observations, and Edwin Hubble with his observation and his graph, his plot. Einstein's field equations, another scientist, Alexander Friedman, who took Einstein's general relativity and applied it to the universe as a whole. Willem de Sitter, and of course Georges Lemaitre. And all together we have the answer that the universe is expanding. Now the fact space can expand is probably not too surprising when we remember from general relativity that gravity is just the warping and bending of space-time. So space can bend, stretch and warp. And so that's why in 2018 the IAU voted to rename the Hubble Law to the Hubble-Lemaitre Law in recognition of Lemaitre's work. Of course, we quite often still call it the Hubble Law and the Hubble Constant just for short. It's quite a mouthful, but it's nice to remember that Lemaitre had a large part in it all. So our results so far, it was pretty clear that the spiral nebulae were actually other galaxies like the Milky Way, and that most of these were rushing away from us at speeds relating to their distance. They were too large, fast and distant to be within the Milky Way, but the fact that the Cepheid variables were found in the other galaxies show that they were actually galaxies.
Running this all backward in time, we would find that the universe must have been much denser and hotter at an earlier time, at a time when it must have started with what we call the Big Bang. So why, of course, couldn't all this just be an explosion in space with us at the centre? You'd think that would make just as much sense. Why does the universe have to be expanding to explain it all? Well, here's a couple of explosions in space. You can see these both have an edge with nothing outside, and the density changes moving out from the centre. But we don't see either of these situations in reality. What we do see is this. So we see a constant density in all directions on large scales, and it looks the same in every direction and from every location. So this is called the Cosmological Principle, which says that we're not at any special location in the universe, and in fact there is no special location in the universe. It's all the same on large scales everywhere in every direction. And here's another way that you might like to think about this. So if we imagine a simple two-dimensional universe on the surface of a ball, with these white dots being our galaxy clusters. Now remember, our universe is not a ball, and it's not two-dimensional, but it's a good analogy to do it this way. So on the surface of our ball here, our two-dimensional universe, all these clusters have to move away from each other. You can see that if this universe did not increase in size and everything was moving away from everything else, you'd end up with some position where everything would have to start bunching up, and in this case on the back of our ball here. And of course we don't see that. We see in every direction, every part of the universe, everything moving away from everything else. And the only way in this example universe is for them all to be moving away if the whole universe is expanding. And if we stay with our simple two-dimensional universe and run it backwards in time, eventually things must get so dense and hot that everything in the universe becomes a hot plasma. A plasma is a state of matter where it's so hot that electrons cannot stay around atoms, so the atomic nuclei, the protons and the neutrons, and the electrons are all separate and don't form atoms. And if that's the case, we should be able to verify the whole process of this expanding universe and even the Big Bang by looking for leftover radiation from about 380,000 years after the Big Bang. If this started off as infrared light here, which we know would be the radiation emitted from the plasma when it cooled enough for atoms to combine, we'd see this getting stretched as it moves across the universe to longer and longer wavelengths, just like the cosmological redshift that we saw previously. And so it should have started as infrared, and it should now look like microwave wavelengths. So we should be able to find that, and it would prove all of this. And here it is. This is the whole sky from the Planck collaboration, the Planck Satellite. This is actually microwave radiation at a temperature of about 2.7 degrees above absolute zero. This started off at 380,000 years after the Big Bang as infrared radiation at about 3,000 degrees. And if you could see microwaves and we could turn off all the lights and remove all the stars in our galaxies, you'd see this in all directions. If you could determine very small differences in frequency, you'd actually see this pattern here, differences of only about 1 part in 100,000. So these are the hotter areas, the red and orange, and the blue areas are the cooler areas, but such a small difference that, as I showed you there, it's only 1 part in about 100,000. So the expansion of the universe stretched the light. So here's our infrared as an example. Stretched the light 1,100 times, so that it's now become microwave radiation with a lot lower energy. This also actually means that the universe has expanded 1,100 times since that radiation was released. Now, to finish up, I just want to say a little bit more about the Hubble constant. And you'll remember from earlier that Hubble calculated this at about 500 kilometers per second per megaparsec, and this was later corrected to around 70 kilometers per second per megaparsec. Now, the Hubble constant is not actually constant over time, so it's actually called the Hubble parameter, and it's been decreasing over the history of the universe. Right now, it's always constant through space at any particular time, so at a particular time we can call it a constant through space. And right now we call it h0, where the naught means at the current time. So the Hubble constant is h0 at this point in time. Now, what does that actually mean? So it's the expansion rate of the universe per unit of distance, and the unit of distance is the megaparsec part. These two clusters are 1 megaparsec apart, and so they're moving apart at 70 kilometers per second. So if we take our Hubble law from earlier, we can see that the Hubble constant here is 70 in this example. We're 1 megaparsec apart, and so 70 times 1 is simply 70 kilometers per second. Anyone on this side will see this one moving away at 70 kilometers per second, and the same looking the other way. And it continues, so if we have our clusters 2 megaparsecs apart, we just say 2 times 70 is 140 kilometers per second, and all the way down here we have 10 megaparsecs. So the distance is 10 megaparsecs, so we see that the recession velocity is what we call it, when you see the other cluster moving away, is 70 times 10 gives 700 kilometers per second. And of course you'll probably all want to know, what about getting close to the speed of light? Well, at a distance of 4,283 megaparsecs, using 70 as the Hubble constant, the separation speed is actually going to be the speed of light. And at nearly 56 billion light years, the separation speed is 4 times the speed of light. Now you might wonder what's going on here, because things can't travel faster than the speed of light. But that's okay, because objects actually have to travel through space at speeds lower than the speed of light. But there's nothing to stop the fabric of space-time itself from expanding as fast as it likes. And this relationship between distance and recession speed works everywhere in the universe, and that's part of the cosmological principle. Now, 70 is not the actual value, and there is a small problem. Astronomers can now calculate the Hubble constant in various different ways. One, as we've seen, is using the Cepheid variables in the Type 1a supernovae, and that's by looking at the nearby universe. There are other options as well, other methods as well, other objects we can use for distance. This gives us an observed value of the Hubble constant at about 73 plus or minus 1 kilometer per second per megaparsec. But using the cosmic microwave background radiation that we saw before, the early conditions of the universe can be used to calculate what the Hubble constant should be now. This uses those different sizes of these spots, temperature spots on the microwave background, which in turn tells us a lot, including average distances between galaxies and the makeup of the universe itself. It combines all this with other things such as the best model of the universe, which is currently something called the lambda CDM model, which is actually dark energy and cold dark matter. And using these calculations, we should see the Hubble constant now somewhere around 67 plus or minus a bit. That's what we should see, but we don't. We see this 73. And the difference is probably a little bit easy to see in this graphic. The difference is called the Hubble tension, and you can see that the local values show it somewhere between 72 and 74. The calculations from the early universe, which are actually very good and very precise calculations, and are very hard to fault, give us between 66.5 and 69.1 with nothing in between. So even the error bars don't cross. And that's the Hubble tension. And as I said, the early universe calculations are very precise. And so that's quite a surprise that these don't match. In May, Chris will actually give you a talk about this problem as well. So we're getting near to the end now. So a quick summary of tonight's talk is in order. Now, we've seen the universe is expanding, and we've seen how we know this through spectroscopy and distance measurements and others as well. And this was really the product of the work of a lot of astronomers and physicists. We've also looked at some of the evidence for expansion and for the Big Bang itself. And this includes the cosmic microwave background, or CMB for short, the cosmological principle, where the universe is the same everywhere on large scales, and also with Hubble's law. And there's also much more I didn't have time to talk about, including the ratio of the elements in the universe, such as hydrogen and helium, which are predicted by the Big Bang as well. So obviously there's a lot more to learn, and not the least is to solve this Hubble tension problem. Now let's just take one last look at the expansion from different locations in the universe. These are the same groups of galaxies at two different times, an earlier time and a later time. We can compare what you would see by overlaying these, and if you lived about here, you would see everything moving away from you. It look like it's all moving directly away from you. But if you lived over here, you'd also see the same thing, everything moving away from you, or here, and so on. So everywhere in the universe, it's the same. Just the same two images are centered on different locations. This, of course, can only happen in an expanding universe, as we saw. And I just hate for anyone to go away thinking that the universe was a ball or a flat sheet. So just to clarify here, on the left, we have two of the two-dimensional universe models that we use through the talk tonight. This top one is a curved two-dimensional universe on the surface of a ball. So in this analogy, there's no inside or outside of this ball. There's no third dimension. And this is two-dimensional curved space. At the bottom, we've got a flat two-dimensional universe. And of course, our universe has 3 dimensions of space. So these are two-dimensional, but this is our one over here. We actually have 3 dimensions of space. But of course, you can learn a lot from these two-dimensional analogies as well, a lot easier to visualize. Our universe has our 3 dimensions of space, plus, of course, time. And our universe is actually a flat universe, but you can have 3-dimensional space, which is curved, but it's actually a whole other talk, so we'll leave that one tonight. So that's the end of tonight's talk, and I'll leave you with this cool animation courtesy of the Sloan Digital Sky Survey. And thanks everyone for listening. Has anyone got any questions?
Thank you, Jonathan. That was really interesting. Yeah, we do have a few questions. There possibly is time for people to get in with a couple more quick ones if you do it straight away. The first one's from Mike, and this is one I was going to ask you to explain a little bit more if nobody asked any questions. It's a bit of a lengthy one, but I'll read it out. He says, it seems counterintuitive for space in a gravitationally bound set of galaxies not to be stretched, but for all the space in between them to be stretched. Where exactly would the boundary between stretched and non-stretched space be? And then he goes on to say, what would a body experience on either side of this boundary, or more interesting if it straddles the boundary? There's a little bit more to that, but if you maybe just start from that.
I was actually thinking about that myself as well. It's something that you can't really find easy anywhere. No, everyone seems to kind of sweep it under the rug a little bit. Probably if you think of the universe as like a system of coordinates, so if you think of a grid and the expansion of the universe, think of the grid expanding. And let's say one of our galaxies is on one of the parts of the grid where the lines are crossing. Essentially, well, the galaxies would be pretty much like points in that situation, but I know exactly what you mean. Why, whereabouts does it suddenly start expanding, and where is it not expanding? I've actually listened to someone called Leonard Susskind, and he talked about it and was asked the same question, and he said that what's actually happening is that the expansion of the universe is still trying to work, say, within the room that you might be in and within the gravitationally bound area. But the gravity obviously is far too strong for it to pull anything apart, and even the other forces between particles. But he described it as thinking of a spring with just a tiny little change in the equilibrium position, probably microscopic or subatomic. And so I suspect, and I can't actually give you an exact answer on this one, but I kind of think that once you get outside the gravitationally bound part, it must almost be expanding fairly uniformly. But don't forget, it's also very small amount on even a scale of a light year, the amount of expansion per second is very small. So that's about the best answer I can give you, is to kind of think of the grid situation and kind of think of it as the grid almost sliding out from under the galaxy, which is not quite right because of the fact that it's all just warping of space. So hopefully it gives you something to go and look up and just kind of use that information to go and have a bit of a look and see if you can find a better answer. But it is a question that no one seems to really clearly talk about. So great question, but I can't give a great answer.
Thank you for that. There's another comment here from Matt, and he says, my kids are loving this and so am I. So thanks. And he says, my daughter would like to know if light can be green shifted.
Well, it can be shifted to green. What they mean by red shifted or blue shifted is just the direction it's going in, and they really just use red and blue as the kind of base words, really. So it's really just towards the blue end and towards the red end, and it's always just shifted some direction. So you could start off with blue light that could be shifted to green, but you'd actually still call that red shifted because it's moving towards the red end. So if that makes sense, it's all just the direction of shifting. Probably a better way would almost be if we said it was shifted to shorter wavelengths and longer wavelengths, but because red is longer than blue, the words red and blue are actually used. So a little bit confusing there, but hopefully that answers that question.
Thank you. Mitchell wants to know, is it a coincidence that the galaxy with a recession velocity of the speed of light has a travel time of almost 14 billion years?
That's no coincidence at all there. That's pretty much right, yeah. So you can, without drawing a little diagram, it's probably hard to explain, but yes, that is exactly the point. If we didn't, because we have dark energy, it kind of changes things a little bit, but if we didn't have dark energy, and the universe was 13.8 billion years old, it would be pretty much the 13.8 as well. So that is not a coincidence, and does match up quite nicely. In fact, the anything that's 13.8 billion years old would actually be about 46.5 billion light years away now due to the expansion of the universe. So the light we see from distant galaxy of, let's say, 13.4 billion years old is actually now in reality probably out to the 40 billion light years away due to the expansion. So anything past that 14 billion light years is going to be receding too far for any new light to be reaching us now. So there is definitely a connection there.
And the final question, this one is from Anne, and she wants to know, why do we assume that the gaps in the spectrum will be the same from every galaxy? And are the elements present everywhere? And if so, why?
Right, that's a good question too. So the elements are the same all throughout the universe, and we can tell this partly from the distributions and from the light we see from various stars. Also the fact that it's the same in every direction. So if we look, say, to the north at a distant galaxy and to the south to a distant galaxy, we can see that it's the same in every direction. And although you could say, well, maybe it's different in time, if it's just different with distance, it would be a very strange coincidence if it was the same for each distance in every direction away from us. We can also see from other things happening in the universe that atoms must work the same. It's actually a principle of quantum mechanics, actually, that gives us these spectral lines. And we know quantum mechanics is also the same throughout the universe as well. And just very quickly, it's to do with the electron's energy around an atom. They can only have certain amounts of energy. And when a photon of the right amount of energy hits the electron, it can bump it up to the next level. And then when it falls back down, that's when it emits that particular wavelength. So we know the atoms are the same all through the universe. And we also know that the atoms are reasonably well spread through the universe uniformly on large scales. So I hope that answers that one. Not too technical, I hope.
Thank you very much, Jonathan. That's the last of the questions on the chat. So thanks once again for a really informative talk.
Thank you very much.